Okay, as always, if you have any questions as I'm going today, send a comment in the chat. Otherwise, I'll get going. There really shouldn't be, this probably won't be too long. I don't have many example problems at hand to do, but I think this quiz shouldn't be too bad either. There's only really one new topic you have, and the other stuff is just an extension of transfer functions. So the two things that will probably be on your exam, honestly, might only be one of them. We'll see. Um, so with transfer functions, this would just be like a holdover from the last unit, kind of. But we'd be talking about the corner frequency. And as a reminder, the corner frequency is when h of omega is like 1 over root 2. But in practice, what you do is you take your h of omega and turn it into standard form. I can't spell. Turn it into standard form, and then whatever you get in that 1 plus j omega over omega c, whatever ends up there is going to be your corner frequency. So I'll show an example of that. That's just something that's been on some previous quizzes. I'm honestly really not sure what's going to be on this quiz. All I know for sure, like I think Zorman mentioned that it might honestly just be two linked inductor questions. I'm not sure. There's definitely going to be like a mutual inductance question though. That's all I can tell you for sure. So that's what I'll talk about more here. So mutual inductance. So if I have some circuit and it has an inductor, crazy. We use this little dot notation to signify like what side of the inductor is linked with what side of another inductor. So as a reminder, inductors in real life are this little coil of wire, and when you run electricity through it, it makes a magnetic field go around it. And this magnetic field can interact with other inductors, right? So if I had some circuit that was like this, and this magnetic field permeated out like woo woo, right? It would end up going through this inductor and causing some kind of voltage to be induced into that inductor by just like one of the laws in physics. I forget which one. Maybe I think Ampere's law. That sounds right. Um, that's probably why they're called inductors, because they can induce stuff in other inductors. That would make sense to me. But the way that we model that in this class is if we have one inductor and current flows through it. So let's say we have current flowing through it like this, right? And when we're doing the math, we turn this all into the frequency domain. So this would be like, I don't know, like 3J. I'll call this like 5J. This can be like 10 ohms, and this can be like 10 e to the j0, or just equals 10. Um, so here, right, and then what we'd say is, so this inductor exists on its own, right? This inductor exists on its own. This inductor exists on its own. However, they interact with each other through what we call the mutual inductance, which we define in this class as some like kind of imaginary other inductor that has currents act on it. So here, oh no, I'll say M equals 2J. And I think the easiest way to explain this is to do a KCL loop, no, KVL loop. So like you were doing mesh current. So if we call this like I1 and this I2, right? Then around I1, we have our, negative 10 plus 3J I1. And then the way that we account for this other inductor is we say, okay, this inductor here, this inductor has some current flowing through it like that. We've defined I2 as flowing through it like that. And the dot notation means that if we have current flowing here, then this is going to induce a positive voltage like such. So you can think of it as like when you have this here and we have our mutual inductance M, then this to the other inductor would be like adding a one of these in parallel with it or in series with it. So this would be equal to if we had I don't know m equals some kj, sure. Then this would be equal to, I times m. This will make a lot more sense when I do example problems. It's kind of hard to explain well. If you need it explained well, look at the lecture notes. He did his best, and I think Zorman, having taught this 20 years, can probably give you a better drawing of this than I can. So anyway, with this specific example, right, what we have though is, so for this first loop, we have our -10, 3j times I1, and then what we'd have is we'd have this 2j times negative I2, and it would be negative I2 because here I2 is going in on the negative side, right? So everything stays positive if it goes in on the plus side. Then if it goes in on the plus side, if the current goes in on the plus side, then this becomes positive and this becomes negative. However, here, since I2 would be going in on the negative side, then this would be negative and this would be positive. And when we go from negative to positive, that means we have a negative thing. That's just passive sign convention from like the first unit. So here, this would be minus 2j I2 equals 0. And I know it's kind of weird because we have I2, even though it's completely like a separate loop, but it still works. And then for I2, very similarly, now we don't even have a voltage source. It would just be 5j I2 plus 10 I2 plus now this mutual inductance here in this side will account for the field coming out of this side and inducing something in this. So it would be plus, this time though it is plus, actually I think it'll be minus as well here, just because of the direction we're going in. This is why Zorman recommends to actually draw things on your notes. So here, the current's going down, which means, or it's going in the dotted side. So then we'd have a plus and a minus here. However, again, since we have our current, our I2 current is going like this, then that means we are going from low to high, which means that this will be negative. Hopefully that made sense. Sorry if it didn't. Again, I will just do more practice problems and hopefully it'll make sense somewhere along the way. And here, though, this mutual inductance will induce a voltage based on this I1. So you end up with the two terms from this actual loop, and then one term kind of from the other loop. And this should not be 5. This should be a 2, because that's what I had defined M as. Okay. So that's kind of a overall view. I think, let me see if there's like a nice table I can copy from his notes real quick. This is the wrong thing. This could be it. Ooh, yeah, that's a very big table. Um, if you're curious, I'll just write this down here. Look at page 6 of lecture notes from 12/02/24. You can find those all in Canvas under the files section. Okay. And then the thing that makes this difficult, though, is that you can have circuits, right, where it's not in separate loops. So we could have it like this, where, oh no, they're actually connected here. But these two are still the ones that are coupled. So we'd say, we have our mutual inductance equal to something, right? And then you'd end up doing the same procedure as the previous one. It's just now it overlaps somewhat. And it can get really messy if it like one inductor was here, because then instead of just having an I2 here, like this one would be flowing through there, you'd have, in this situation, you'd have like an I1 minus I2 flowing there. But I think I should be going over one of those in a minute, if I remember correctly. But yeah, I will just go to the example problem. So again, this is probably going to be a shorter than normal review session, just because last one of the semester, there isn't really too much new content, and I don't have any practice problems readily available for me for this semester or for this quiz. But yeah, if you have any additional questions, again, be sure to let me know. Okay, so this is our thing, and we are saying write the mesh current equations. Or it'll say, yeah, write all the equations. Actually, in this question, it says write all the equations to find voltage drop across 10 ohm resistor. Okay. So what we do here is kind of the same thing we did before, just more complicated now. So what we have, let me make sure I'm looking at this correctly. Okay, yeah. So if we call this I1 and this I2, I'm going to make this lowercase because I like writing lowercase i's more. So I1 and I2. So about this left loop, the I1 loop, we'd have minus 20 plus 2 I1 plus J4 I1 plus 10 I1. And so that's all the normal stuff, right? Oh, and I actually messed it up because I'm forgetful. J4 I1 minus I2, that's just normal mesh current stuff. I just forgot. Plus 10 I1 minus I2. Okay, and then you would have the mutual inductance part. So here we look again. So here we see that this imaginary or this I2 flows this way through the inductor, which means that the dotted terminal is going to be negative. Remember, if it flows through the dotted terminal, then the induced voltage has the if it flows in the dotted terminal, then the induced voltage is positive on the other dot. So this case is the other situation. So since it's flowing in from the non-dotted side, then our dotted side is negative. So it's like that. So we have this extra term here, which is going to be equal to, oh, and I forgot to write the mutual inductance is J2 ohms. So here we have our mutual inductance times I2. So we have J2 I2. And here, since we have a voltage rise in the direction of our I1, in terms of this loop, this would be negative. And then we say that equals 0, and that's our first equation. For I2, we do something basically pretty similar. So we'd have, I'll start with that 10 ohm resistor. We have 10 times I2 minus I1 plus J4 times I2 minus I1 plus J6 times I2. I don't know why I actually wrote out times there. J6 I2 plus or minus J3 I2 plus 4 I2. And now we do our mutual inductance part. So here we have plus, let me make sure I'm doing this right before I write it down because I don't want to be silly. answer key here that I have says something that I kind of disagree with. Let me look at something real quick. Um, just a second. Okay. Yeah, I think it's just again with the mutual inductance term, we look at how the current is flowing through here, right? So what we have then is one part is going to be, so we have our J2 term, right? And then from the other loop, we'd have I1 minus I2, and that would be flowing down that way. And that would induce a positive here and a negative here. And again, this is opposite the direction, or it's with the direction of current flow, so this will be negative. So here we have minus J2, I1 minus I2. And I think that should equal 0. Let me make sure I'm doing this right again. But hmm, plus J2. Oh, that's what it is. Okay. So there's actually one more term, my bad. Because this would be the impact of the other loop with the mutual inductance. And then we'd have one more term, actually, which is going to be the impact of this loop on the mutual inductance, I think. Wait, that doesn't make any sense. I think this answer key is just wrong. Yeah, I'm going to decide this answer key is wrong and say that that equals 0. Okay. So again, as a recap, what we have is for this first loop, we have, basically you just take your normal stuff if you're doing a normal mesh current. And here, we have our normal mesh current. And then we have our kind of add-on term, which is what is induced. Oh, that's what it was. Okay. Sorry. I lied. The answer key was right all along. Um, so here I'll notate this a bit more. So this is the J6 mutual inductance. So this is from this current affecting here. However, here this is the J4 affecting J6. So that's going like that, where it's this current and it induces a voltage here. But then the one I missed was we also, even though we already talked about this in the other loop, we would have this one affecting this, because this one is still in this loop. I should have reviewed this myself a bit more before I came. That is on me. But I can give better explanations if people need, but hopefully that makes enough sense for now. So here, if we look at this, right, we have our I2. Let me erase these blue things that I've written. Okay, so here, so hopefully you see where this term came from, right? And then we have our final term here, which is going to be how the current flowing through here will induce something on here. So we have our I2 flowing like this. It's going into the non-dotted side, which means that the dotted side will be minus and this will be positive. And here, what we have is that we have the current flowing in the direction of the voltage drop, so it's positive. However, key thing to recall though is that both of these are going to have the impedance value of J2 because they both are just the mutual. So this will be plus J2 I2. And that would be your final thing. And then since the question is asking about the voltage drop over the 10 ohm resistor, then we'd have that, V10 ohms equals I1 minus I2 times 10. And that would be your final answer. Just these three equations. Yeah. That's going to be like, it's probably going to be, the question on the quiz is probably going to be almost identical to this, if I'm being honest, because like this is the most complicated thing you can ask without it being too much, I think. I can't really imagine him doing more than that. He always can, I guess, but yeah. And then I'll do one other question that was on a previous quiz, which is about transfer functions. This is our source voltage. Got a little op amp. Got okay, and it's saying part one, find corner frequency, and two, find the magnitude of the transfer function at three times the corner frequency. So what we have to do first is, find the transfer function. So if we want to do that, we would have same way you did op amps before. You know that Vn is zero because Vp is zero. These are both 0 volts. So then we have, 0 minus Vs over 1K plus 0 minus Vs over, and then that 1 microfarad is going to become, oh, actually that makes a bit more sense. The answer key here that I have that I am making sure I don't mess up off of did it all in variables, which is kind of more useful to see, I think. So we have 0 minus Vs over R1. This is R1, this is R2, this is C. So 0 minus Vs over R1 plus 0 minus Vs over J over omega C plus 0 minus V out over R2 equals 0. All of these are going to get moved around a bit. So we'll have Vs or negative Vs times 1 over R1 plus this will flip. So it'll be 1 over J over omega C, and 1 over J over omega C is going to be negative J omega C, I believe. Yes. Yeah. So I'll write that in the next step. And then you'd add over this V out. So this would be V out over R2. And then we want to find V out over V in. So let me simplify this a bit more. So you'd have minus Vs times 1 over R1 minus J omega C. And this is a negative, sorry, equals V out over R2. And then if we want to solve this for V out, or solve this for V out over V in, you do some algebraic manipulation. V out over, and by V in, I mean Vs. V out over Vs here is going to be, if we move this here and multiply that over, you get, these negatives are going to all cancel. So you'd have 1 over R1 plus J omega C times R2. And then we want to get this into standard form, which means that we have to make the real parts equal to 1. So that means we want to multiply by R1 over R1, which would get us, or we want to, is that right? wait, you want to, oh yeah, you just factor out 1 over R1. So if we factor out 1 over R1, then we would get, make sure I'm still doing this correctly. Yes. You'd get 1 over R1 times 1 plus, if you factor out R1 from J omega C, you'd get J R1 omega C R2, which would be R2 over R1, 1 plus J omega over 1 over R1 C. And this step is just because we want to have this in the form of J omega over omega C because this is our corner frequency. So that's going back to like what was on the last quiz with corner frequency and standard form of a transfer function. So here then, we know omega C equals 1 over R1C, which equals 1 over R1 was 1K times 1U, which is going to be 1 over, yeah, it would be 1 micro is 10 to the negative 6, so it'll be 10 to the 3 times 10 to the negative 6, which would be 1 over 10 to the negative 3, which is 1,000 radians per second. So this would be your transfer, or this would be your, the first part of the question, that would be your corner frequency. And then it says find h of omega at 3 times the corner frequency. So if we want to do that, what we do is we'd say, okay, the magnitude of our transfer function, and does it say to get it in? Oh yeah, in dB. Okay, so the magnitude of our h is going to be 20 times the log of the thing that we had, R2, R1 plus J omega over 1 over, I'll just say 1 over, come on, omega C. And then if we use log rules to expand this out, we'd get 20 log R2 over R1. Let me, um, oh, I have one too many negatives in here. This should be a negative on those. Okay. But that doesn't really affect anything. So we'd have minus R2 over R1 plus 20 log, and this would actually be the square root of this with each of these squared. That's just the definition. I just forgot to do that. Oopsies. I think. Yeah. Yeah. So then if we did this, it would be the log of 1 plus J omega over omega C, 3 omega C, which is equal to 20 log minus R2 over R1 plus 10, because this is to the power of 1/2 here. So 10 log 1 plus J omega over 3 omega C squared. And then we know what all these values are now, so we can just plug it in. So if we plug in R2 and R1, 20 log negative 4K over 1K, if we look back at that initial problem up here, plus 10 log 1 plus, and here omega would be, oh, that's what okay, this is not supposed to be a 3 because the corner frequency stays the same. Function stays the same. My fault. Function stays the same. Then what we do is we plug in J3 omega C over omega C squared, because we're saying when omega equals 3 omega C. So then the omega C's will cancel. this is J3 squared. So this would become 1 plus J3 squared, which would become 1 minus 9, which would be, is that right? Oh, there's not supposed to be a J in here anymore. I'm rusty on my complex math, apparently. So because we are taking the magnitude, the J's all disappear. I'm fumbling left and right now, but I will get to the right place in the end. So this would become 1 plus 3 squared, which would be 10 log 10. And this is 20 log negative 4. And because, again, because we were taking the magnitude, oh God, I messed this up so much. Okay, let me skip back a couple steps and make this a bit clearer. Because okay, so this was our initial thing, right? We got from the previous part of the question, we got our transfer function as 1 plus j omega over omega c, where omega c equals 10,000 or 1,000. So we have this, and then we want to do 20 times the log of its magnitude. And the magnitude of this is going to be the magnitude of the first part times the magnitude of the second part. The magnitude of the first part, the magnitude of a constant is just a constant. So this is 20 times the log of R2 over R1. That's just going to be its absolute value. I'll split this up a little bit. And then 1 plus j omega over omega c. And then since this is a complex number, when you take its absolute value or when you take its magnitude, you do it like this. That's just the definition. Okay, then you simplify it down to here. This is supposed to be a positive for the whole time. So if we do 20 log 4 plus 10 log 4, you get 12.04 plus 10, and that's 22.04 decibels. And that is the magnitude of the transfer function when you are at 3 times your cutoff frequency. Sorry, that was a bit of a hassle. Um, yeah. I don't know if this is going to be on your quiz. Like, I think when I was talking to Zorman, he did just say you're probably only going to have some mutual inductance questions. So it could just be that. My advice is to look at I forget if there was any on the homework. If there was some on the homework, just look at the homework solutions or look at the examples he did in class. That's probably your best bet. Does anyone have any particular questions? So I don't really have much else to go over. Let me check the homework solutions to see if there's like something there I could just do. Uh, let's see. Uh, okay, I mean that's like, well, that's kind of evil, but okay, I'll do this question from the homework, but only do the writing equations part because that's all that would be on a quiz. So here we have okay, and then we have in this question you have actually two sets of mutual inductances. Hopefully you all did this on the homework, and so you have somewhat of an idea of what I'm doing here already. but I know it can be useful to have someone like properly do it for you. So here, let's pretend this is a quiz, and they were asking us to write all the equations necessary to find the voltage over this 4 ohm resistor. So we'd have two current loops. And in this first loop, again, remember, you always want to start by just writing like the normal mesh current thing. So we got -10, 4I1, J3I1, J4I1. Okay, and now we have to do all of the mutual inductance terms. So this J3 is going to have a mutual inductance from the J4. Let me move this all down so I can draw my little plus and minuses. So we're looking at this on this. So here we have, okay, I1 travels downwards through J4, which means, or it's going in the dotted side, which means that it's going to cause a positive here and a negative here. So if we look at that in terms of the passive sign convention, okay, that means it's going from low to high in the direction of current, which means it's going to be a minus J1 times I1 because it's going to be that mutual inductance here. And then for the other one, I'll use red for this. I1 is going through here. It's going in from the non-dotted side. So that means the non-dotted side is positive. So we have it like that. And this is going from low to high as well. So this is, again, going to be minus. So this is minus J1 I1. So we have two of those terms. And then last but not least, we have how this one affects this one. So here we have, okay, I2 goes in the non-dotted side. So then our non-dotted side is negative, or our non-dotted side is positive, and the dotted side is negative. So this last term is also going to be negative. So here we have negative minus J2 I2, and that equals 0. So that would be the left loop. And let me actually look here and make sure I did that all right. Yes. Yes, I did. Okay, cool. So then I2 is going to be a bit simpler because there's only one mutual inductance here. But again, we start by writing out just the normal mesh current equation. So J6I2 plus 2I2 minus J2I2. That's from the capacitor there. And then for this last one, I don't have enough colors. I'll use purple. Okay. So we have the effect of this inductor through here by way of this. So again, the purple current, so I1 is going in the dotted side, which means that it's going to induce a positive at the other dotted side. So what we have here then, current is going that way, and that current is rising in the direction, or the voltage is rising in the direction of current, which means this is a negative voltage. So this is going to be minus J2 I1 equals 0. And then if we want to find, the voltage across this 4 at the end, you just say, V 4 ohms equals 4 times I1. So let me color code this in case it'll make a bit more sense. Okay. And that would be your final answer if this was asked on a quiz. So it is very useful to draw these little pluses and minuses. It'll help you from making mistakes. Don't try to do it all in your head like I was doing at the beginning. It doesn't really work out. Yeah, I don't have any other practice questions to do, so either if you have any questions about the homework, speak up. I'll give you guys like 10 seconds to respond. Okay, in that case, enjoy your Thursday night. Um, you know, study for tomorrow, but make sure you're ready for the end of the semester. I hope my review sessions have been helpful this year, or this year. Yeah. Good luck on your final quiz. Good luck on the final. And yeah.